Hello YouTubers, and welcome to the next in the series on solar power. Now in this video what we're going to concentrate on is looking at charge controllers versus grid tie versus DC optimizers versus microinverters, and to try and understand where they fit, the pros and cons and things you need to look out for. Now, during the preparation of this video, I thought certain of these technologies were going to be relatively straightforward to explain, but as I dug a little bit deeper, even I discovered there are little nuances and ways in which certain technologies work even under the same banner, which can potentially affect the pros and cons and the benefits. Now, one of the other challenges with these newer technologies, in particular the DC optimizers and the microinverters, is that they haven't been around for a long time. They started making their appearance in the 90s, but they kind of came to market in around 2008, 2009, but probably only in the last 2 to 3 years has there been a larger installation of them. But still, in 2 to 3 years, that's not a lot of time to fully understand their reliability and then to gather enough data to understand how well they perform in different parts of the world. You may find that someone has done a lot of data gathering down, let's say in Australia or South Africa, but that data doesn't necessarily match up with the performance that might be expected in somewhere like Europe or in the north of America. But anyway, we're going to have an overview, understand the high level workings of these, and then in time to come, I hope to get my hands on the individual products, because that is where the particular nuances will come out in terms of the particular products and how they perform. Now, what I'll do to start is just talk about some of the bits and pieces that I've had in various installations in the homes that I've lived in. And when I started off having solar power in our first home in Tumbers Kloof, there was no talk about having a grid tie inverter. It was just a case of having an MPPT charge controller with another inverter and then a bank of batteries, because I wanted a backup system. And typically you might have something like this Outback Power Systems MPPT charge controller. A few years later I went and purchased this micro inverter, but this is a cheap Chinese inverter. It's actually fairly heavy, and this needs to be connected to the back of your solar panel. It then takes the DC from the solar panel and converts it directly to household AC. Now at the time, the interesting thing was I did an exercise and I worked out that these cheaper micro inverters, if I had, let's say, a 2,500 watt system and I required 10 of these, the system cost then, because these were cheap, would cost less having 10 of these than one big grid tie inverter, which was a fair outlay in cash, versus 10 of these. Things have changed, and these micro inverters have got smaller, lighter, more efficient and more robust in terms of their longevity. However, just realize they haven't been out in the field a long time to give a proper track record of how long they will last, especially in testing environments. Right, so let's start talking off about the charge controller. So that Outback charge controller would be a typical device that could be installed on a solar power system. Typically these days, that kind of system would be on an off-the-grid situation. Let's say you've got a cabin in the woods which isn't near the grid. So let's explain how it works and where potentially it might be used in an on-grid situation. So looking at this diagram at the top here, we've got some solar panels which are linked together in a string. And this is one of the things which does become important, because depending on how you link the solar panels together, whether in series, all chained together, or in parallel, potentially has an effect on the kind of voltages you're going to see coming into your inverter or your household. Also potentially the reliability and how well the whole system can function. Now typically what you do is string a few solar panels together in series to get a certain voltage level, which is the optimum for the system. Now when I say optimum, if you're out in the woods and you're looking at, let's say, running DC appliances, which makes a lot of sense because then you can have better efficiencies. You don't want too high a voltage coming into your charge controller, because the more it has to do a DC to DC conversion between, let's say, a higher voltage to a lower voltage, you're going to get more losses in the system for the most part. In a system, let's say we've got a 48 volt system where you might be feeding into an inverter, then you're obviously going to want your voltages coming out of your solar power system and into your charge controller as close to that as possible, Obviously, it's going to do the DC to DC conversion to optimally run the solar panels using MPPT to get their maximum power point, but then convert that voltage, which is hopefully close enough so there are not too many losses, to, let's say, run your 48-volt battery system. Now in this diagram, I've got the panels linked together going through the charge controller, which directly feeds the battery or charges the battery because it outputs DC. And in this situation, the most efficient use of your energy then is to take out and run DC appliances. But of course, because you've got a battery involved, there are significant losses involved in a battery. And that's where battery technology can be important. Your standard lead acid batteries tend to have a reasonably high internal resistance. Lead crystal batteries have a lower internal resistance, and the best battery technology for low internal resistance are your lithium technologies at the moment. But if you need to run AC applications, then you may have to draw the DC out of your battery and go into a DC to AC inverter. And in a log cabin, you may be in a situation where you cannot have all your appliances that run off DC. You know, some folks these days obviously want a big screen TV, it's AC, so that's where you'd need that inversion. Now the next system I'm going to explain, because we're going to revert back to the charge controller system, and that is the grid tie solution. And that's probably one of the most common installations that are happening today. And what you have is you obviously have a string of panels, and the idea here is that you string quite a few panels together to get a higher voltage. The higher voltage you get coming out of that is beneficial in two regards. For one, a higher voltage means less current that has to be carried by the wires. If you have to carry a higher current through the wires, you get greater losses. Also, that higher voltage means that your grid tie inverter is going to have a better time of inverting a higher DC voltage to, let's say, the higher AC voltages that are required for households. Now, if you're in a normal household and your appliances are AC, this would obviously seem like the more logical route to go. If you had the system up here in a normal household where you've got a charge controller, well then you coming in DC to your charge controller, you're then going into a battery, you've got losses, and then you're then going out into inverter to be converted back to AC. So there are lots of losses along the way. Whereas in this system, you're going straight from DC to AC to be used by appliances in your house. But there is one interesting scenario where this system may be better in a grid-tied situation. If you have a normal household like myself, where let's say I work from home and you've got appliances running during the day, whether it's aircon or pool pumps, then it makes sense with a grid-tie inverter that you're using your AC straight away for those things running during the day. But let's say you happen to be a person who lives in a climate where they don't need, let's say, much heating or cooling during the day. They don't have computers running, so their household is not using much AC electricity. So then in that case, let's say they want to use their energy at night time, they have to have a battery storage system. And then it makes sense to go straight from DC to charge your battery and then using that energy at night, rather than having a grid tie solution where you're going DC, AC, inverter, back to DC, charge battery, and then out of the inverter again at night. There are more losses involved. So you really do have to look at your usage and the potential losses involved. Right, so looking at the most of the installations these days which are using grid tie inverters, what are the challenges with this setup? One of the big ones is that you've got a whole lot of solar panels chained together in series. Often you'll have multiple strings, so you'll have a single string because you often have a maximum voltage allowed for your grid tie inverter, a maximum DC voltage. And then you'd have to have a second string linked together in series and then joined in parallel to come into your grid tie inverter. Now, if you have any shading on any one or more of these panels, that potentially brings down the whole string. You've got a single maximum power point tracking device in your grid tie inverter, which is controlling this whole string. It sees it as one virtual solar panel. It doesn't see the individual solar panels. So it's trying to do MPPT across all these panels. And that's why it's important that you use the same type of panel and that they're all matched. Now, for one, you're not going to know whether from the manufacturer that they're performing exactly the same, but they should be close enough but they need to be closely matched, or else the MPPT is not going to be able to do a good job. And if you have any differences across any of those, like for instance, if you have a roof which might be facing one direction and another part of your roof which is facing another direction, you're going to have different lighting on those panels. And that is a problem for this kind of setup. Also, if you have any break in your wiring or a solar panel that goes down, then that also potentially takes down the whole system. So that's where we get to now our DC optimizers and our microinverters. Right, so looking at our DC optimizers, these provide a cost-effective way of providing control to each and every solar panel so that it can be optimized for the lighting that it's getting. For the most part, these DC optimizers have their own MPPT tracking on each of the solar panels, so each of the solar panels can be individually monitored. However, as I said at the beginning, some manufacturers do this in different ways. Now, for the most part, they'll still be linked together in a string, and if you're doing the MPPT at each of the panels, it provides you with a far more flexible system so that in different light conditions, each of the panels is performing at their optimum. It also means that you can potentially put different types of panels in here because each of them will be optimized, and then their DC power is brought to a central inverter. Now, the goal for these DC optimizers is to basically try and keep a single DC voltage level that comes into an inverter. And the way that some of these companies implement their optimization is different. Some do just a simple DC to DC conversion at the panel and then have an inverter over here which does the MPPT. Some of these technologies employ impedance matching. They'll actually change the impedance at the panels so that if there's a problem, the power flows around a panel and voltages are adjusted accordingly to get the optimum voltage level for the inverter. Now, in certain of these setups, let's say for instance you've already got a grid tie inverter, some of these technologies you can just go and add on to your panels and they'll work with your grid tie inverter. But the other types of these technologies, where let's say they're doing more specialized MPPT at each of the panels, they require an inverter where they've got a single voltage input because the MPPT work is being done at the actual panels. They bring the DC in at a specific voltage level and that goes into a single point over here. So therein lie, when I talk about a single point, therein lie some of the challenges, is that when you do have these single points like you do on a system like this, if that fails, everything goes down. Some of these systems, even though you've got the panels linked together, do have ways of routing around a panel which is, let's say, failed. So if you've got a panel which has got a problem, or one of these DC optimizers which has got a problem, it can be eliminated from the system. And some of these systems employ special gateways which communicate with the optimizers to see what's going on and to adjust their performance. And that's how they can be eliminated from the system. This often isn't clear when you go and read about DC optimizers, the way that they work. And so I'll add links below which further explain the different manufacturers and how they implement this optimization at a panel level. The one added feature about this versus, let's say, going to microinverters is that the cost of optimizers ranges anywhere from $30 to $70 per panel. And that's a lot cheaper than your microinverters. Your microinverters, generally speaking, are going for $100 to $250 per panel. Also, what I have seen in some of the optimization solutions is that you can tie 2 solar panels to a single optimizer. Now, you obviously perhaps lose the benefit in that both those panels are controlled by a single optimizer, but it's better than having a whole string controlled by a single charge controller. It does also allow some design flexibility. With the previous systems, you really had to calculate your voltage in your strings so that you didn't overrun your grid tie inverter. They were specified for a certain voltage level, and you had to make sure that your open circuit voltage on a cold day was a measurement that you had to take into account. Whereas these systems can employ both buck and boost, sometimes not both, but they can either boost the DC voltage or drop the DC voltage. So let's say you have an inverter here which is rated to handle 800 volts. You could design a string that works at 1000 volts and on a cold day might hit 1200, 1300 volts. And these optimizers will then drop the voltage level to get the right optimized voltage to that inverter. Now you heard those levels I was talking about. That's the one thing to be aware about, is that you can still potentially have high DC voltages in a system like this, and then cabling potentially can be a challenge. In the one system where I said it does impedance matching, those voltage levels tend to be low. They tend to be around 30-35 volts. And what it does is, let's say one of the panels is shaded and is providing less voltage, it will increase through impedance matching. It'll increase the voltage, operating voltage of the other panels to still try and sustain a good value DC voltage coming into the inverter. As an added safety on some of these systems, and it's something to look into, is that because you could potentially be sitting with very high DC voltages on your panels if you've got a disconnection. Let's say you're going to do maintenance and you go and switch off your inverter. You could have a very high DC voltage at this point. But often they've got safety built into the optimizers where if they don't see the inverter, they'll then shut down their production. And that's certainly something to look for if you are looking at these kind of solutions. So the next solution is our microinverters. Now the beauty about the microinverters is that, for one, they are generally connected in parallel. So you could have a solar panel go down or a microinverter go down, and the rest of the system is still up and running. They'll each have their own MPPT, so each panel is optimized for its varying conditions, whether it's shaded and the others in the sun. Also, it allows for individual panel monitoring. Just like the optimized system, many of these systems have a monitor which allows you to see how each of the panels is performing and can highlight an issue if one of your panels isn't performing well. The beauty about the microinverter system for the most part is that you can obviously have mismatched panels. You can also grow your system after you've installed it. You may only have the funds to, let's say, install 4 panels right now. You can then go and add another leg and add another 2 panels next year, and then another 2 panels the following year. And those panels don't have to be the same as the ones you originally have, which is a problem with the original, let's say, grid-tied or charge controller systems. They have to be designed specifically for a string length and having all those panels in stock. And the microinverter system allows you a lot of flexibility. It also means that you've got 220 volts, your household AC, 220 or 240 coming off the panel, which allows more flexibility in your cabling systems. You don't have to have a lot of copper because you're carrying a higher voltage at lower current. One of the things to also look for is the string lengths that you are allowed in these systems. In the DC optimized systems, some of them state you need like a minimum of 8 panels in a string to run. Now for me, that would be a problem because I'm starting out with a set of 4 solar panels. So that would be a limiting factor that you need to be aware of. Most of these systems also obviously have a maximum depending on the type of system you're running. So you need to look at any minimum requirement and maximum in terms of the panels in a string. With most of the microinverter systems, they don't have a minimum. You can have 1 panel only. But they certainly do have maximums because there's a maximum amount of current which can be carried along this mains cabling. The other thing to be wary about with these systems is that often they'll have a monitoring device. Now that monitoring device can be like this little Envoy controller that I've got for my N-phase system. Now this system, what it does, it communicates with the panel so you can individually see the performance of each of the panels. It can log any problems and it can send it off to a website on the internet, so that can be individually monitored, and you can keep logs of your power production, and as far as I know this can be done locally as well. Now one of the things to note about systems like that where you've got a little monitoring box is some of these companies have been charging for that service. They will charge per solar panel. So that is something you want to cater for because those costs can obviously add up over time. At the moment, as far as I know, Enphase in particular are not charging, but verify that before you go and jump into it. Also, Some of these systems, particularly let's say the DC optimized systems, that is potentially another single point of failure. You obviously got your main inverter, but you've got a monitoring box which might be in here, and if that goes down, your DC optimizers won't operate in some cases. In the case of the microinverters, in theory it looks very nice in terms of robustness. You haven't got a single point of failure in terms of an inverter because all your inverters are sitting on your panels. You do, however, have that monitoring box in the case of N-phase. And in the case of N-phase, at your initial installation of your solar panels, the system needs to be configured for the power system that you're running in your country. And you need that Envoy gateway to do that. After that is done, I think it purely acts as a data logging device, and the system will still work without it as far as I know, but it's something to be aware of and to double check. And I say, once I get into the further detail of the individual products, that is something I'll highlight because that could potentially be a gotcha. The other issue in terms of failure points with a microinverter system is that your solar panels are sitting in the sun and they're potentially getting very hot. If you're doing full MPPT, DC to DC conversion, and then DC to AC conversion, those microinverters are working and generating heat themselves. Plus they're on the back of a hot solar panel. And that potentially means a good reason for failure. That's why they have to be very careful in terms of the kind of components that they use in these systems. Electrolytic capacitors will dry out, so they have to use other types of capacitors. What some manufacturers have elected to do is split off some of the electronics from those microinverters. Now, as an example, I'll talk about SMA. And what SMA have done, they also have microinverters that they've literally just brought out in the last year. And their microinverters will do MPPT and optimize each panel for you. And they'll generate AC onto a common bus. They have something called a multi-gateway. And that needs to be there to finally provide the AC to your house. They say by doing this, they're removing some of the electronics which are at risk to heat behind the solar panels and bringing it to a central point over here. One of the benefits with a normal microinverter system is that your single points of failure are potentially ruled out of the system. Whereas here on the SMA system, if your multi-gate inverter goes down, then your whole system goes down. So these are the things to be wary of. Now in terms of costs, obviously the DC optimizers per unit tend to be cheaper. They also tend to scale better as well. The costs on the microinverters are linear. You've got a fixed cost per microinverter, but apparently there are solutions for the DC optimizers that make it more economical once you start growing and scaling it. But again, you have to be aware that you've got these strings tied together and the limitations there. So in terms of the cost, there's a new term that is being bandied about because it can sometimes be very difficult to understand if you're spending more in one area. Like for instance, if you're spending a higher capital cost on your microinverters, potentially your installation costs can be a lot less. There's a lot less work involved in designing a system like this and potentially installing it. Whereas the previous generation systems required a lot of upfront design and wiring costs may have been an issue. So to understand the benefits and the cost analysis of all of these is something called LCOE, or levelized cost of energy. And what you do is you take the overall cost of a system like this. And when I say overall cost, even let's say the cost of shipping it to you. Like for instance, if you have a large, let's say 5,000 watt array, the shipping weight of all the individual microinverters will be far more than let's say a single big inverter. And so that needs to be taken into account for systems like this as well. But what you ultimately need to do is take the complete cost of a year, the complete power production, let's say over 25 years, and then normalize that or level it across the entire investment. And that's of course very difficult to do because each installation is going to have different energy production and different challenges in terms of the installation. One of the things that I mentioned about kind of putting costs over 20 or 25 years, that's the other challenge, is that a typical standalone or centralized inverter will have a guarantee or warranty for about 5 or 10 years. And what the microinverter crowd have been doing, they've gone and up. They initially started out with smaller warranties on their equipment, they have now moved up to 20-25 year warranties. But of course, they haven't been in the field that long to really prove themselves. So you certainly want to be wary about, if you are going to go the DC optimized route or the microinverter route, do not buy cheap. You certainly want to go with a name brand that you know will be around in time to come, because we don't have a full understanding of the potential failures, particularly in warmer climates. Right, then the other thing to note with, in particular, say the kind of microinverters and DC optimized or optimized solutions on each panel, as I mentioned, is these gateways. For one, you need an internet connection if you want to gain the benefit of seeing the performance across an entire array and see that it's performing correctly. That is one of the advantages of those systems, is that you're going to have each panel performing at its best. And you're only really going to gain that advantage if you're able to monitor it and see that each panel is performing at its best. And that's where these systems come into play. You need to have an internet connection, you need to have a gateway, and your data potentially is going to be stored by a third party. And that may of course raise privacy issues. So you want to see whether you can have a local data collection system, so that if you don't want to have to opt into a third-party web-based solution, that you can also do it locally on a PC in your own home. If you are willing to go with a web solution with a third party, check and see if there's any costs. Check and see whether you have to have a gateway there operating after the fact, after installation. If the gateway fails, will your system still be up and running? Right then, so before we end off, what about the future? Now, the one thing I have mentioned before, which will be coming in the future, is actually AC panels. So at the moment, when I go to install the system that I've just purchased, I have to take these N-phase microinverters and mount them on the back of the solar panels, and then go and mount them on the mounting system. There are things you have to take into account, like the earthing of the solar panels and these microinverters. And the one benefit of these 4th generation N-phase microinverters is that they've got an integrated grounding system. So in theory, you don't have to have a separate copper wire grounding the system together. But I still have to go and mount these on the back of panels. Now in the future, it looks like solar panel manufacturers are going to move to having integrated microinverters or optimizers on their solar panels, and that'll make installation and design a lot easier, specifically for the DIY folks. As long as you've got a mounting system that you can go onto, you can far easier go and just plug panels literally onto your roof and potentially plug them into your main system or your grid in your house, and you're up and running. Now when I say that, it sounds very easy. With the old DC systems, or let's say the charge controllers, you had to be very wary of having proper switch gear, DC breakers, and ways to eliminate switch off the power in an emergency. Those things do become simpler once you have your microinverters, or let's say even integrated AC power production directly from the solar panel. But you still need to be aware of the safety coming into your breaker box, your DB board, and then also going out onto the grid, and the implications of doing that with your own power company. Some power companies allow that, some power companies don't. So I will follow up with another video talking about the implications of bringing that AC power into your house, how you get it out onto the grid, the split phase voltage system that's here in the States, and perhaps even talk about some of the challenges in other parts of the world, in particular in South Africa, where people have some of the older meters and spinning meters backwards and gaining credit that way. That poses some interesting challenges for the homeowner and the electrical company providing power to your home. But anyway, I hope you've gained some value from that. If you do, please give us a thumbs up, and I'll catch you soon for the next video. Cheers.